guys, welcome back to my channel. Please remember to like and subscribe. Now today we're going to be looking at complex numbers and polynomials, and we're going to start with a simple quadratic equation. So let us say we have z squared plus 2z plus 2 equals 0, and my task is to find z. Alright, the first thing we'd naturally attempt to do is to factorize this quadratic equation. But as it is, it can be factorized, so we're going to have to use the quadratic formula. The quadratic formula says that z is equal to negative b plus or minus square root of b squared minus 4ac all over 2a. So z would be equal to, my b value is 2, so that's negative 2 plus or minus the square root of 2 squared minus 4. My a term is 1 and my c term is 2, all over 2 times 1. Z becomes negative 2 plus or minus the square root, and that's going to be 4 minus 8, that's negative 4 over 2. Now, earlier I would have learned from previous content that we can now find the square root of a negative number. So what I'm going to do is to separate this. So I'm going to say that z is equal to negative 2 plus or minus the square root of 4 times the square root of negative 1 all over 2. Z would be equal to negative 2 plus or minus 2. And of course, we said that the square root of negative 1 is represented as I all over 2. So z is equal to negative 1 plus or minus I. Now let us separate these answers. Z equal negative 1 plus I, or z equal negative 1 minus I. Now there's a special relationship between these two roots. If you look at them carefully, you realize that they are conjugates. Now notice coefficients are real numbers. If we go back to the quadratic equation, z squared plus 2z plus 2 equals 0, a is 1, b is 2, and c is 2 as well. But the roots are complex numbers. Now bear in mind that from symmetry of roots of equation, we would have learned that there's a connection between the coefficients and the roots of the equations. And probably we can make a deduction here, so we're going to do a small investigation now. Alright, let us see what happens when we use conjugates to try roots that are conjugates to try to find the original quadratic equation. So this says find a quadratic equation whose roots are p plus qi and p minus qi. Now let us see what we remember. The general form of the quadratic equation is z squared minus alpha plus beta times z plus alpha beta equals 0. Now of course alpha and beta represents the roots of the equation. So we can call the first root alpha, and we can call the second root beta. Alright, let us populate the equation. So I'm going to have z squared minus, this is p plus qi plus p minus qi times z plus p plus qi, put that in a bracket there, times p minus qi, and all this is equal to 0. This becomes z squared. Now bear in mind from our previous video what happens when you add two conjugates. And as you can see, it's simple to work out. It's just going to be 2p, which is just 2 times the real part. So this is going to be z squared minus 2pz plus, when we multiply two conjugates, we have the real part squared plus the imaginary part squared. So I'm going to have p squared plus q squared equals 0. Now if you examine this carefully, you would notice that there is no I in there. All i's have been eliminated. So here is a very important deduction that we can make. We can say the complex roots of quadratic equation with constant coefficients occur in conjugates. All right, let me put that in words here so we can know that. What do I mean by that? The complex roots of equations with constant coefficients occur in conjugates. Let us go back to the previous question that we did. It was z squared plus 2z plus 2 equals 0. And the roots were 1 plus 2, well, sorry, that would be negative 1 plus I and -1 minus I. These are the roots. These are complex roots. But let us examine the coefficients. A is 1, B is 2, and C is also 2. And by constant coefficients, we mean that coefficients are all real numbers. The roots will naturally occur in conjugates. Alright, here's an example of a question that typically tests the concept that we just covered. It says, given that 1 plus 2i is a root of z cubed minus z squared plus 3z plus 5 equals 0, find the other roots. Now, for this particular equation, if we notice that the coefficients are actually real numbers, you have a being 1, b being -1, c being 3, and d being equal to 5. The root that we are given is 1 plus 2i, which means that the second root will actually be the conjugate. So my second root would be the conjugate of that, which is 1 minus 2i. Now, once we have two roots, we can actually create a quadratic factor. It is a cubic equation, which means that it has 3 roots. We have 2 roots already, so we can create a quadratic factor. So let me start by doing this. Bear in mind that we said it's going to be z squared minus alpha plus beta times z plus alpha beta equals 0. Now we can even skip the entire process because bear in mind alpha plus beta would be 1 plus 2i plus 1 minus I. And when we add two conjugates, it's just 2 times the real part. So this simply becomes z squared minus 2z plus what happens when we multiply two conjugates. It's the real part squared, which is 1, plus the imaginary part squared, which is 2. And all this is equal to 0. So this breaks down to z squared minus 2z plus 5 equals 0. So that is my quadratic equation, but my quadratic factor. So my factor is z squared minus 2z plus 5. Now, how do I get the third factor? There are several ways that we can go about doing that. We can do long division, we can do comparison of polynomials, we can even do trial and error. Alright, let's go with long division. Just remind you from unit 1. So we're going to have z squared minus 2z plus 5 into z cubed minus z squared plus 3z plus 5. So we said the highest power here in the divisor is z squared into the dividend z cubed would be z. And then we multiply z by everything. So this becomes z cubed minus z into z times minus 2z, that's minus 2z squared. And 5 times z, that's 5z. So when we subtract, we're going to have z cubed minus z cubed, that's 0. Minus z cubed minus minus z cubed, that's z cubed. 3z minus 5z, that's minus 2z plus 5. Now z in z squared into z squared, that's 1. So we're going to have plus 1. And then we multiply all that by 1, we're going to have z squared minus 2z plus 5. And right away we realize that our remainder is 0, so we know that our factor is actually correct. Now this implies that z squared minus 2z plus 5 times z plus 1 is equal to 0. And this is how we get our roots. Oh, since we already found the other roots, the only one we need to find now is using the factor z plus 1. So z plus 1 is equal to 0, which implies that z is equal to -1. So we now have our 3 roots. So all my roots would be 1 plus 2i, 1 minus 2i, and -1. Okay? We're now going to look at a question where we have the coefficients involving complex numbers. So it says solve for z in z squared plus 6 plus I all times z plus 10 equals 0. Now, we can't factorize this, so we're going to have to go right ahead and try to use a quadratic formula. Bear in mind that it says that z is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. In this case, my b value is 6 plus I. So I'm going to have negative, put my bracket there, 6 plus I plus or minus the square root of 6 plus I all squared minus 4 a is 1 and c is 10 all over 2 times 1. So z equal, and I can simplify this, I'm going to have negative 6 minus I plus or minus the square root, and the 6 plus I all squared is a perfect square, so we can use a shortcut. So we square the first term, which is going to be 36, the first term times the second term times 2, which is going to give me 12i. And when I square the I, I'm going to have I squared, which I know is negative 1. And 4 times 10, that's minus 40, all over 2. So z is equal to negative 6 minus I plus or minus the square root. Now underneath this, we have 36 minus 1, which is 35, minus 40, which is going to give me negative 5, plus 12i. And all of this goes over 2. Now, this is going to take me to my previous video now, where we spoke about the square root of a complex number. So I'm going to have to take out this part. So I could probably say taking the root of negative 5 plus 12i. We're going to have to find the square root of this particular part. So we can say, well, we can assume that the square root, so let the square root of this be equal to x plus iy. So we can say x plus iy all squared is equal to negative 5 plus 12i. Alright, once again, we have a perfect square. We know what happens here when we expand this is going to be x squared plus 2xy minus y squared equal negative 5 plus 12i. And of course, when two complex numbers are equal, the real parts are equal, the imaginary parts are equal. So this implies that x squared minus y squared equal to negative 5 and 2xy is equal to 12. Equation 1 and equation 2. Now from equation 2, we can say that y is equal to 12 over 2x, which means that y is equal to 6 over x, which we're going to sub in equation 1. In equation 1 in the place of y. So we end up with x squared minus 6 over x all squared equal negative 5. Now when I break this down, I'm going to have x squared minus 36 over x squared equal negative 5, which is going to be x to the 4 minus 36 equal 5x squared. So I'm going to have x to the 4 minus 5x squared minus 36 equals 0. And of course, you'd have known that this is the same equation from the previous video. So to save time, I'm simply just going to write the solution here so we can continue. So from the previous video, just recapping because we don't want to have to go through all this to save the space. Recall that the square root of negative 5 plus 12i was actually equal to plus or minus 2 plus 3i. I'll put that inside of a bracket there. So when I go back to the equation now, it's going to become z equal, we're going back all the way to over the left hand side, which is negative 6 minus I plus or minus 2 plus 3i all over 2. Alright, so we know we have to separate this. So we're going to have negative 6 minus I. Let me go with plus first, plus 2 plus 3i over 2, or we can have negative 6 minus I minus 2 minus 3i all over 2. So this breaks down to negative 6 plus 2. That is going to give me negative 4. And you have negative I plus 3i, that's plus 2i over 2. And then you have negative 6 minus 2, that's z equal negative 8. And then you have negative I minus 3i, that's minus 4i over 2. So therefore, z is going to be, if we say 2 into negative 4, that's going to be negative 2 plus I, or z equal 2 into negative 8, that's negative 4 minus 2I. So these would be my roots. And of course, you do notice that these are far from being conjugates. They're not even similar. All right, and why did this happen? And that is because we would have noticed from the original equation, z squared plus 6 plus I times z plus 10 equals 0, that the coefficients do involve complex numbers. All right,